single cycle microarchitecture today, and I hope we'll make a start on microcoding as well, multi-cycle architectures. Let's see. But first of all, you turned in your homeworks, hopefully. The solutions are already posted online. I hope you're following the website. We're trying to, well, Chris and Lavanya and Adir are trying to update it as frequently as possible. Take a look at the solutions and see if your answers are correct. Homework 2 is already out. You realize it. It's due February 13th. And it's going to cover a lot of the things we've already covered. ISA concepts, ISA versus microarchitecture, and some on microcoded machines. You may not be able to do this question right now, but you'll be able to do that question hopefully at the end of next lecture. Okay, this is very important. If you haven't started Lab 1, you're already very late. Who hasn't started Lab 1? Or who has the guts to raise their hand right now to this question? Okay, if you haven't started, you should start. Or if you're done, you should be done very soon. There's lab assignment 1.5. This is not really an assignment. It's for you to practice your Verilog or brush up on your Verilog. It's not to be turned in. It's for your preparation for lab assignment 2, which is our first Verilog-based assignment. Essentially, you will design a single cycle microarchitecture for MIPS for that. Part of which we will cover today, at least the basic principles of which we will cover today. It'll be your job to figure out exact implementation details for the subset of MIPS that we have given you to design. Okay? But I'll give you the basic way of going about designing it. And it's due February 17th at the end of the lab. Yes?
Is that a solo lab or a...
Yes, this is an individual lab also. Actually, one of the comments, I read all of your statements that you gave me. One person, who shall remain unidentified, I think, said that they would benefit most from the lab if they remained individual. And I tend to agree with that in general. You really learn a lot more if you're individually doing everything. But there may be some labs where you work in teams as well. Just because the sheer amount of work could be very high. But don't get scared, you'll learn a lot. Okay, readings for next lecture. I had already assigned these readings, so hopefully you've done it and have a good idea of the microarchitecture of the LC3B, but we'll cover really the principles as well as the readings themselves in the next lecture. This is essentially a micro-programmed multi-cycle machine, and we will cover those machines in the next lecture. So please read that Appendix C carefully, and this is online. It's actually not part of the book. It's a revised version of the ISA as well as microarchitecture in the book. Patterson and Hennessy Appendix D covers a similar microarchitecture for MIPS. Again, micro-programmed multi-cycle. This will help you as well. We're not going to have you design a microprogram multi-cycle architecture. Microarchitecture. We're going to jump into a pipeline design from a single cycle design. But this is very important for you to know. And there's an optional reading. It's a 3-page reading. It's by Maurice Wilkes, one of the pioneers of computing. Actually, he got the Turing Award for designing some of the earliest computers. As you can see, according to him, the way these two chapters design the microarchitectures for MIPS and LC3B are the best ways to design an automatic calculated machine. And this is the best way in 1951. So this is the first paper that introduced how to design a multi-cycle microprogrammed microarchitecture. And you will learn that very well in the next lecture. But before we get into that, we'll first study how to do everything in a single cycle. Okay, just to get you started, there are some. I read all of the homeworks that you've given me, and there were some questions. This was the most popular question, I think. Maybe 2 or 3 people asked it. Can you do the labs in System Verilog? Unfortunately, no. Our infrastructure has not been migrated to System Verilog, and as I understand it, there are some issues related to the tools or actually the tools have not been tested with the types of designs that you'll be doing, the larger designs that you'll be doing in this course. So if you're not doing the system Verilog, but fortunately, Verilog is similar enough to system Verilog. It's just another language, and they're very close enough languages. It's like C++ versus C, as I understand it. Is that correct? No, it's not? No. Really? Well, we have a handout telling you what the differences are. So I know Verilog. I've done a lot of designs in Verilog. Actually, I have not used system Verilog, but I don't think it should be a big stretch going from system Verilog to Verilog. Just like going from Java to C is not a big stretch, right? As long as you understand the basic fundamentals and principles. You just need to learn how the language works. Okay. Yes, this class will hopefully fulfill your desire to understand how a processor truly works. And hopefully that's why you're here. Yes, it will be time-consuming. But it will also be fun and easy. That is if you understand things. Once you understand things, everything's easy, right? And hopefully the goal is to make you understand how this thing works so that you put in the hard work to translate that understanding to an implementation that actually works. Somebody said, don't you have our pictures already? Yes, I do have your pictures already. It's in the class roster. But I'd like you to give the pictures that you want to give me rather than an official university picture. That's why I asked for your pictures. And I've got interesting pictures also. So there was one person who got the MIPS acronym, who answered the MIPS acronym actually. And I will not give you what MIPS stands for. Do you guys know now? Okay. Maybe that'll be a question later on. Or maybe I'll cover it later on. But one person actually answered in the homework 0. And thank you for that. Okay. Let's review the last lecture before we start. I'd like to try to do this at the beginning of every lecture. Just to populate your cache. So we covered complex versus simple instructions, the concept of semantic gap. We covered the use of translations to change the trade-offs associated with the semantic gap, right? Your ISA could be very close to the high-level language or very close to control signals, but you can add another layer, if you will, a translation layer, to change the classic trade-offs that happen with complex versus simple instructions. And Chris sent out an email pointing you to a file, a PDF file that describes Transmeta's code morphing software and how they change the trade-offs. That's actually a relatively high-level paper, and if you're interested, that's a good paper to read. We covered a bunch of trade-offs in ISA: fixed versus variable length, uniform versus non-uniform decodes, number of registers, addressing modes, unaligned memory access. So hopefully these are coming back to you now. Okay. I guess one question for you. What is the benefit of translating complex instructions to simple instructions before executing them? Remember we had this semantic gap, and I should write bigger. High-level language, control signals, your ISA has complex instructions if the instructions are closer to the high-level language. Now you can have a layer that translates these to more simpler instructions, like RISC-like instructions. And you can execute RISC-like instructions in hardware. This could be hardware. And this translation layer could be hardware or software. Yes?
You might want to do it because then you can optimize how that instruction works.
That's right, yeah. You could do it that way. In hardware, you can optimize just the simple primitives without putting effort into optimizing these complicated instructions. So that optimizes the execution. It also keeps the hardware simple, right? It also keeps this part simple. And that's one of the major benefits. Yes? You were going to say simple probably. Yes?
If the translation layer is hardware, wouldn't that take away the opportunity from Are there two options?
That's right, it could. I mean, it could, sure. If the translation is software, you could optimize in software. If the translation is hardware, then you could optimize in hardware. It depends on where you do the optimization. So if you do, so one other benefit of this is you can optimize the translation layer once, and in different processor generations, you can just optimize this layer underneath. That's what a lot of Intel and AMD x86 implementations do, actually. They translate the x86 ISA into simpler instructions. They call it micro operations. Through hardware, so there's hardware, dedicated hardware on chip that translates complex x86 instructions into simpler, RISC-like instructions. And this hardware doesn't change that much over processor microarchitecture generations because they optimize it quite a bit the first time. Whereas they change the implementation underneath here, the execution of the simpler instructions quite often. And if you look at, for example, Pentium Pro versus Pentium 4, this translation layer is relatively similar in Pentium Pro and Pentium 4. But the execution of these simpler instructions is very different. The microarchitecture, well, this is also microarchitecture, but the part of the microarchitecture that's here changes a lot more frequently. Yes?
You said it inherently had at least one level of this because you have your control signals, and so we take all those together, that essentially forms a micro instruction. So for each instruction, it has multiple cycles. You can just take each cycle as executing some instruction.
I didn't quite understand that. So this micro instruction is different from the control signals. They call it a micro operation. It's really a simple instruction.
Instead of like you have two levels of translation.
That's right, yeah, that's right. That's right. And then you take the simpler instructions and generate control signals out of them, right?
Yeah.
But that's, in a sense, that's really generating the control signals, right? So that's here. That's bridging the gap between these two. Whereas here, you're not generating control signals, you're generating some other form of instruction. Okay? Okay. In hardware, what is the benefit of doing this in hardware? And what is the benefit of doing this in software? I think I'll let you think about this. But do you have a question? Or?
I was going to point to software to make it easy for the application to write on the
That's right, yeah, it's good. If your instructions map well to the high-level language constructs, and I will get to that. Because that point was not clear in the last lecture, right? Okay, I guess another question. Which ISA is easier to extend? A fixed length ISA or a variable length ISA? Variable length, good. Why? Because you can add more instructions more easily if your ISA is variable length, right? You can even change the maximum length of your instructions. Whereas if it's fixed length, you're going to run out of opcodes at some point. Make sense? Okay, another question that we didn't exactly cover, but how can you have a variable length uniform decode ISA? Or can you have a variable length uniform decode ISA? Remember, variable length instructions have variable length. Uniform decode, what does uniform decode mean? Yes?
I think uniform decode means is have a single way of decoding all outputs, not like you have to like jump to separate parts of the output based on what you need to output.
Doesn't just mean that, like, if you're looking at your instruction, they have to be divided up exactly the same. Like,
Yeah.
immediate can't span two like registers that are in like a different instruction.
That's
So
right.
you pull down uniformly. So as long as each instruction strictly builds blocks off the previous one, then you could uniform decode variable length instructions.
So uniform decode is essentially the same bits in the instruction, in different instructions, specify the same things, right? For example, opcode is always between bits 31 through 26. Is that correct? In MIPS? Or something like that. The top 6 bits, right? So uniform decode means that that. So how do you have a variable length uniform decode ISA? But if you have your opcode is basically variable length means your instructions could be this length or this length or this length, right? Yes.
Well, I mean, uniform decode just means that if the field exists, then for all instructions that use the field, it must be in the same place. So
that's good.
So, like, I mean, it's okay to have shorter instructions as long as, like, any fields. I mean, as long as the fields that the instruction needs are present within the length of instruction that you have. So, I mean, like whenever you have a set of instructions that use the same field, you just have to make sure that the instruction is long enough that it will have the position within it.
That's right. So, in a sense, what you're saying is for the given length, you have the same bits specify same locations. You have the same bits specify the same function, if you will. So it's kind of odd to think about a variable length uniform decode ISA really, but if your opcode is, for example, at least the first opcode byte is here, this can be considered uniform decode across different instruction lengths. But normally, a good way to think about this is having uniform decode based on the instruction type. One way is you can divide the ISA as having instructions of different lengths. And for instructions that are 1 byte, for example, you can have uniform decode across all of those instructions that have 1 byte, that are 1 byte. You can have uniform decode across all those instructions that are 16 bytes. Okay. Make sense? You just need to ensure that the bit fields within an instruction type always signify the same thing. That makes decoding easier. Of course, variable length itself makes decoding a little bit hard because you first need to determine the length. So these are kind of related concepts, but they're different. Okay. So you could have that, yeah. You could encode that somewhere, right? You could design an ISA that says the first thing you see in an instruction is how many bytes will come after that. And that's kind of what opcode does implicitly in variable length ISAs. Okay, so but uniform decode usually goes with fixed length because it's hard to think of fields that don't exist, right? And this is what I said before, just to put it down right. In a variable length ISA, uniform decode can be a property of instructions of the same length. Okay. A note on risk versus CISC. I don't think I made this very clear before because we didn't get to it. We covered different trade-offs. Risk, remember, reduced instruction set computer. One big property of it is simple instructions. The goal is to simplify the hardware as much as possible. Well, what other ISA properties go with it, right? Fixed length, uniform decode, few addressing modes. These are really all properties of the risk. Because this all simplifies the hardware. Right? You can see the design philosophy of something like MIPS here. CISC, on the other hand, well, negate each of these. You have complex instructions, variable length, non-uniform decode, many addressing modes. Complex hardware, yes.
Is MIPS for uniform decode? There's at least 4 different decoding patterns.
That's right. So it's very difficult to get a perfectly uniform decode ISA because you really want to specify different things for different types of instructions. MIPS is uniform decode within instruction types. So if you have an R-type instruction, all R-type instructions are uniform decode. But no, and it has few types. So that's what's usually meant by uniform decode. If you want perfect uniform decode, that's very difficult to get. Then your length increases, fixed length increases a lot. Because then you will need to have like an address field in every instruction, even though you don't need it. Okay? Okay. So one more note on semantic gap before we move on. So if we have a small semantic gap, I just want to make this clear. the ISA is closer to high-level language, right? And software's job to translate from the high-level language to the ISA is easy if the high-level language constructs are actually mapping to the ISA. Right? So if you have a string copy in the high-level language, and ISA has string copy, this is great. But if the high-level language doesn't have a string copy, if it has something else, some low-level operations, then it's hard for the compiler to translate, right? So the compiler now needs to do a mapping from some set of operations to string copy, and it needs to figure out these set of operations are actual string copy. Does that make sense? So software job is harder if the high-level language constructs do not actually map to ISA constructs easily. So there's a semantic mismatch in that case, right? If you will. So semantic gap is small if the semantic level of the high-level language and the ISA are close, meaning you don't have primitives in the ISA but high-level constructs, and you don't have a mismatch in the semantics. Semantics are similar. Does that make sense? I wanted to clarify this because we had a discussion in the last lecture where is it easy for the compiler to actually translate from high-level language to a high-level ISA with small semantic gap. It's easy if the semantics actually match. If you say string copy, the high-level language maps to the string copy here. If you say FFT here, high-level language has this construct and ISA has an FFT instruction. Right? If you have polynomial evaluation, for example, and ISA has a polynomial instruction, polynomial evaluate instruction, which some ISAs in the world do have, like VAX. Okay? Whereas if the high-level language doesn't have this polynomial, how do you actually figure out that the code is doing polynomial evaluation, right? That may be tough. That's the idea of semantic mismatch. Okay. Any questions so far?
When we stop at one layer of translation, what would be the disadvantage if we added like 2 layers of translation?
So I'll let you think about it. Yeah, you can go indefinitely, right? You can have many, many layers of translation. Maybe in the next homework you can write why you don't want more layers of translation. So with any layer of translation, there is overhead. I'll give you that much. Okay? But that's a good question. You can have many, many layers here, right? The question is, what value does it add? I know it adds overhead, but does it add much value? You guys can think about it too now. Okay? So last time we covered some of these slides. Let's recover them quickly. So how do we process instructions? Now we're going to implement this ISA. Well, what does processing an instruction mean? It's taking an architectural programmer visible state, and according to the specification of what the instruction does, generating another architectural state. I'll call it AS prime. And these should be AS prime to be consistent. I guess I should really search and replace A and A prime, huh? But anyway, rename in your mind that A is AS, architectural state, A prime is architectural state prime, next state. So ISA specifies abstractly what the next state should be given an instruction. So it's really an abstract finite state machine, right? You have state at the beginning, you have an instruction that does something to that state and produces another state, another architectural state. So from the ISA point of view, there are no intermediate states because that are visible to the program, right, during the execution of an instruction. However, microarchitecture implements how this is done. So there are many choices in implementation, and we can have programmed invisible states to optimize instruction execution, and this will become very clear very soon. You can have multiple state transitions per instruction, right? One way of designing the microarchitecture is really literally following the state machine the ISA tells you, right? You have an architectural state, and in one clock cycle, process instruction, if you will, implements next state logic. Right? It's all combinational. You can think of it as combinational. And you get the architectural state next, if you will. But you have other choices as well. You may not want to take a single clock cycle to do all of this work that is specified by process instruction. And why would you not want to take? Well, if your instructions are huge, right? You may not want to have your clock cycle to be long. And we'll get to this again. You may want to take multiple clock cycles to transform this architectural state to another architectural state. And this is the fundamental difference between single clock cycle microarchitectures and multiple clock cycle microarchitectures. You have intermediate states here. Okay. So a very basic instruction processing engine is really a single cycle microarchitecture. Each instruction takes a single cycle to execute, and only combinational logic is used to implement instruction execution. So let's build such a machine today. And we will have no intermediate programmable invisible state updates. You have only combinational logic that operates in a single cycle. And if you have doubts about if this can be done, leave them aside for now, because we will get back to those doubts. You can raise those concerns after we finish. Well, what we're going to do is basically you have an architectural state at the beginning of a clock cycle, and we're going to process instruction one clock cycle, and we'll have an architectural state at the end of a clock cycle. Okay? And the next clock cycle, for the next instruction, this AS prime will be AS. Okay? And you keep going. There's essentially a loop here. Well, this loop is very nicely illustrated here, right? You've seen in 240. You've figured out how to actually design combinational logic. You've figured out how to design sequential logic, state elements. And think of your state elements as your architectural state. And this is the process instruction, combinational logic that can process any instruction that's specified by the ISA. Make sense? So let's design this. Well, I guess I'll throw this question out there. What is the clock cycle time of this state machine determined by? Yes?
The depth of the combinational of the logic.
How long it takes, the critical path of this combinational logic, right? How long it takes. What is the maximum logic delay through this combinational logic? Plus, what is the maximum delay to actually latch the signals into the sequential logic? Because there is always some delay in latching. And you've seen this in 240, right? It's not zero. That delay is not zero, so you need to account for that delay. So clock cycle is really determined by the delay of the longest or slowest logic path within this combinational logic, plus the latch delay. Okay? So that's the low level. Now think of this as an instruction processing engine. Combinational logic really implements the processing of an instruction. So at the higher level, what is this clock cycle time determined by? What determines the maximum logic delay for this combinational logic? If your combinational logic actually is implementing the processing of an instruction. Yes? Time taken to process that instruction. That's correct if you're implementing only one instruction in this combinational logic. But this combinational logic is supposed to implement all of the instructions, right? Yes? Exactly. The time that is taken to implement the processing of the slowest, I'll rename it that way, slowest instruction determines the delay of this combinational logic. And hence, that determines your clock cycle time. Yes?
Does that mean that x86 will be running at about 3 hertz because of the root rather than that speed?
Keep that in mind. We'll get back to it. Okay, so keep this in mind while we discuss this microarchitecture. Well, I guess we already went through this step. What is the critical path of the combinational logic determined by the time it takes to process the slowest instruction? Okay, let's leave that aside for now and let's see how we can implement this machine. What is the state? What are we talking about when we talk about programmer visible state, architectural state? Well, it's memory, it's registers, and it's the program counter, right? At least for the microarchitecture we're going to study. And you've seen this slide before. And we're going to take this and transform it to another state in the next clock cycle. And we know, I mean, this architectural state tells us how things are going to be transformed, right? Because you have a program counter. That's pointing to the memory location, which contains the instruction that's going to be executed in this clock cycle. So your state is complete, really. Okay. So I already told you about this. All state updates are made at the end of the instruction's execution. The big disadvantage is this. Right? The slowest instruction determines the cycle time. So you have a long clock cycle time because your instructions may be very long, as you pointed out, right? Eric pointed out. If you have a repeat move S, are you going to have your clock cycle combinational logic designed to actually implement all of the functionality required for repeat move S in one cycle? Think about it. Well, is that even possible, first of all? I don't know. But stretch your imagination and things. Whereas in multi-cycle machines, instruction processing is broken into multiple cycles, stages, and state updates can be made during an instruction's execution. Yes?
Is it possible to have the clock cycles depend on the instructions, so you have a variable clock cycle length? So like it wouldn't be generated by like a crystal, like a quartz clock or something.
Okay.
So because then you can.
I don't know if that's considered a clock at that point. That sounds more like an asynchronous.
Yeah, well, it's just
logic,
a
right?
clock signal, and like some guy just pressed the button and it was the exact clock.
Okay. I like your thinking, but I think that's more like an asynchronous logic, right? Essentially, you have what is asynchronous logic, right? You determine how long it takes to execute something, depending on you determine when things get updated, depending on when things finish, right? So you need some handshake to actually ensure that that works. Okay. And that's another way of building a machine, right? So through asynchronous logic, which we will not cover here. Okay, state updates can be made during an instruction's execution in a multi-cycle machine. Architectural state updates made only at the end of the instruction's execution. Advantage over single cycle, now the slowest stage, if you will, determines execution time, right? Determines the cycle time, clock cycle. So these two machines both follow the von Neumann model literally at the microarchitectural level. And this will become more clear when we get to pipeline machines. So these are still fetching, executing, and finishing single instruction at a time. Both single cycle and multi-cycle machines. Whereas pipeline machines will fetch, execute, and finish multiple instructions at a time. Okay. So before we get into designing this machine, let's remember the instruction processing cycle. You read this in one of your readings. Instructions are processed under the direction of a control unit, step by step. Right? An instruction cycle is really the sequence of steps, or stages, if you will, to process an instruction. And fundamentally, there are 6 phases, or steps, to do this. You need to fetch the instruction. You start with the program counter pointing to the instruction in memory. You need to fetch it. You need to decode it, figure out what it does, or what it should do. Well, you need to evaluate the address, memory address, required by it. You need to fetch the operands that are needed by the instruction. You need to execute the instruction. You need to store the result back somewhere. And not all the instructions require all 6 stages. For example, some instructions do not store results. A jump instruction. Jump instruction really needs fetch, decode, and evaluate address. Assuming you don't need to fetch the operand from memory or register. In a single cycle machine, all 6 phases of the instruction process cycle take a single machine clock cycle. In a multi-cycle machine, all 6 phases can take multiple machine clock cycles. In fact, each phase can take multiple clock cycles to complete. Okay? Let's view the instruction processing in another way. I just want to give you the different ways. So this is, you process instructions according to some stages. And these stages are fundamental. They may or may not exist for some instructions, but this is what you will follow in any design. But how do you follow it? Basically, you follow it. An instruction transforms some data to some other data. Right? You can think of architectural state as data. And this transformation is done by functional units. These are units that operate on data. And these units need to be told what to do with the data. And who tells them what to do with the data? Well, this is the fundamental distinction between control and data. Basically, an instruction processing engine, if you will, consists of two components. One is a data path. These are hardware elements that deal with what's happened to the data signals that are input. For example, functional units that operate on data. This is part of the data path. Or hardware structures that decide the flow of data. Where should the data go? Into the functional units, into the registers, into memory, and what data should go there. These are wires and muxes. Muxes determine what data you're going to operate on, right, in the functional unit. And we will see this very soon. And storage units that store data are part of the data path also, registers or memory. These all deal with data. Now this says nothing about how these muxes are configured, right? Which mux do you choose? Which input to the mux do you choose? So you have an ALU, for example. One example I'll give you is the one input of the ALU could be a register coming from the register file. But the other input could be an immediate value, right? A sign extended immediate. And you need to choose the output based on which one you're operating on. So there's a control signal to this mux. I guess mux control, I'll say. And this control signal needs to choose either the register or the immediate, depending on something that's happening in the machine. And what is that something? Which instruction is being processed, right? Let's say this input is always a register. And you know, in MIPS ISA, there are instructions that are R-type, and there are instructions that are I-type, if you will. I-type instructions operate on immediates. For example, you can have an add I that adds, I guess, register source to immediates, sign extended immediates specified in the instruction, and stores the results into a register destination. Whereas R-type instructions, you can have an add that adds RS to RT and stores the result into our destination. Okay. Let's say you have only one ALU. Now, the control of this mux is determined by whether this instruction is an add I or an add, right? So the control logic, there's some logic here, if you will, and I'll call this the control logic, takes as input, I guess this is the instruction, bytes, and outputs what the control signal for this mux should be. Should it be 0, indicating that the input coming from the register file is selected, or should it be 1, indicating that the input coming from another part of the data path is selected? This depends on whether the instruction operates on an immediate or a register as its second operand. Make sense? So this is control logic. Another example of control logic is, what should this ALU do? Right? You have a control signal, I guess ALU control, I'll call it. Well, in this case, it's a 1-bit signal, right? In this case, it may be multiple bits, depending on what kind of functionality you have in the ALU. Well, you have an add instruction. You could have a subtract instruction, for example, right? And this could be encoded in as part of the instruction bytes. And those instruction bytes that differentiate between add and subtract determine what this control should be. Okay. If this is, let's say, I'm going to make this up, but if the instruction that's being decoded is an add, then the control signals, let's say you have 4 functionalities: add, subtract, I don't know, shift. Let's remove shift for now. XOR and AND. And 0, 0 specifies an add. 0, 1 specifies sub. 1, 0 specifies XOR. 1, 1 specifies AND. So let's say you have a 2-bit control signal. If the 2 bits are 0, 0, this ALU logic selects to do add. Okay. If these 2 bits are 0, 1, this ALU logic selects to do subtract. Make sense? So the control signals are generated based on what the instruction specifies. And this is control. Control signals dictate what happened to data in the functional unit. Okay? And in your lab, you will design this control logic. I won't give all of this to you. I'll give some of it. But you will design this control logic as well as the data path. But these are 2 distinct components. They merge at some point, and you will see that. Okay. These are essentially hardware elements that determine control signals. Basically, signals that specify what the data path elements should do to the data. What this MUX should do to the data inputs it receives. What this ALU should do to the data inputs it receives. You could, for example, in the register file, one control signal is write enable, right? Let's say you have one port to the register file, and you have several inputs. This is source register, another source register, and the destination register. If this write enable signal is asserted, then the register file writes the data input, there's a data input as well, into register D. Register specified by this register at the index, register D. Okay. So whether or not this write enable is asserted, again, is determined by the control logic. And how does the control logic determine that? Well, if the instruction we're processing is supposed to write to a destination register, then this write enable signal is asserted. Okay. And this is easy to do in a single cycle machine, right? You basically look at the instruction bytes and assert the write enable signal if the instruction is writing to a register. Yes?
Say you're doing an add and your destination and your RS are the same. How would you do that in one cycle? Because it seems like the write enable would be enabled to be writing to something you're also reading from. You end up with some sort of weird circular logic where you still...
I see. So that's a good question. That's one of the things that we will punt on in this lab. We'll assume magic register file and magic memory. But in a real system, that's an absolutely correct question. So how would you do it? Say it again. Latch it. Exactly. So one way of doing it will be not building a single cycle machine, right? But this basically, when you're reading a register, you don't write to it, right? So that could be one way of doing it, right? You disallow in the ISA, but that doesn't happen. Okay. One other way of handling this would be to detect this condition, right? So how do you detect this condition? You check whether any of your sources are the same as your destination. Right? Yes?
Is the register file just like a series of registers, and each register have a clock manipulate?
That's right.
So you can read the current register, and you assert read enable so that it's not for the next clock cycle that it will be modified. So
That's right, yeah.
There shouldn't be any conflict.
Yeah, it could do that. But if I think I understood your question as, what if this thing is happening in the same cycle, right? Or what if somebody's trying to write to the same register? So what happens is, it really depends on how this is implemented. So if your write enable takes effect at the end of the clock cycle perfectly, then this is not a problem. But when you write enable, the signals transition, and if you're write enabling the same register that you're reading from, you may get garbage value, right? Because signals are transitioning during that time. That's the magic register file assumption that we're having, right? Guys?
We have multiple ports.
In the lab?
We have multiple ports.
Oh, you have multiple clocks in the lab?
Multiple ports.
Multiple
Ports.
Oh, okay. There are multiple ports in the lab.
Yeah.
Okay.
It's still magic, though.
Yeah.
What do you mean still magic?
Single cycle.
It's single cycle.
It's what?
It's single cycle.
Okay, it's single cycle. Yeah. So in the lab, the assumption is that you will get the correct value. But this is a real problem that we will get to later on. Okay? Does that answer your question? Okay, good. All right. Let's look at control versus data in single cycle and multi-cycle machines. In a single cycle machine, control signals are generated in the same clock cycle as data signals are operated on. So here, in the same single cycle, the control logic determines the control signals as well as while the data is flowing. Right? Whereas in a multi-cycle machine, usually control signals that are needed in the next cycle can be generated in the previous cycle. Because you're going through states. In the next cycle, you need some control signals, and you can generate them in the previous cycle. Which means that latency of control processing can be overlapped with the latency of data path operation. And if you read Appendix C, you've seen this. Okay. How many people have read Appendix C for LC3D? Not yet? Oh, you have. Okay, good. So you have seen it for all. Okay. So there are many ways of designing this data path and control. You will design it in a particular way in the lab. But it could be single cycle, multi-cycle, pipelined data path and control. You could have a single bus design versus multi-bus designs. You could have a data path that consists of a single bus that contains the data. And see your homework 2 question for this. Now you cannot do this easily with a single cycle design, if you will. But with a microcode design, you will see that. You can have control signals generated in a way that's combinational, or this is called hardwired, or combinational control. Basically, you have combinational control logic here. Or this control logic could be a control store, if you will. Which means that you index with the instruction and to a memory, and the memory provides you all of the control signals you need. And we will see both designs. Today we will look at the more hardwired combinational control. But you could imagine the control signals to be generated by accessing memory. Does that make sense? You have a special store that contains control signals based on the instruction bytes. You take the instruction bytes, generate an address into this control store, and this control store gives you what control signals you need for that instruction. Okay. And control signals as structure, of course, depend on how you design the data path. So, for example, if in your design you don't have this box. So this is one way of designing the register versus immediate. Right. What is another way? Well, you could have another ALU, right? So I don't know how to do this one. Okay, there is a way. Oh, this doesn't go. So this is design 1, if you will. You have register, immediate, and you choose between them. Whereas design 2 could have multiple adders, right? You can have register, register, and you can have register, let's call this RS versus RT, and immediate, and you can put the mux here at the end, right? That's certainly possible. Well, in this case, I guess the control signal will be the same. But now you have different control signals to specify. Now, if your instruction is an immediate, you would like to choose the result here. Let's say 0, 1. I guess, is it an immediate? This is an instruction, I guess, I type, as we will see. So what should your control signals be in this case? If this is an I type instruction. You don't care, right? You don't care what this ALU does in that case, because you're going to choose this result anyway, if it's an I type instruction. So you can set these control signals to X, if you will. Don't care. If it's a register type instruction, you would like to choose this output. So you set this control signal to 0. And you set this control signal to the ALU function that's specified by the R-type instruction. And these control signals then can be don't care. So these are two different designs to accomplish the same task. Of course, this has less hardware, right? So which one would you choose? You'd probably choose this one. This makes no sense in this case, right? Okay? When would something like this make sense? Well, in a single cycle microarchitecture, it won't make sense. But it could make sense if you're crossing multiple instructions. Right? You can use this ALU for some other purpose, right? While using this ALU for another purpose. So if you're having concurrency. For example, you may be doing multiple instructions per cycle, right? Then it could make sense. You will need to provide some other data path here, of course. Or this ALU may be used to compute, I don't know, the jump target of a jump while you're also executing another instruction. Okay? So in that case, it could make sense when you have concurrency. But if you don't have concurrency, then this design is wasteful. Right? You're wasting hardware. Okay? Okay. Now let's take a closer look at a single cycle microarchitecture. I've given you some of the building blocks that will seem familiar. Remember, we're going to implement this. Well, we're going to start with some state elements, some of which I've shown before. I guess we have the program counter. This is our state element. And it takes an input, and it provides an output. And input, in this case, is always left at the end of the clock cycle. So during the clock cycle, the assumption is that the values are stable. The values of the previous state are stable. Registers, you have, I guess, for MIPS, you have 32 registers. So you can have the read register ID, the second register ID, and the destination register ID. The data that's to be written to the destination register. And these are the output ports for the read data. And there's a write signal, write enable signal that I showed you before. And this is asserted, this should be asserted when you actually write. We're going to separate memory into two, instruction versus data memory. Instruction memory operates this way. You provide an instruction address and you get the instruction output. Data memory is a little bit more complicated. You provide an address, which gives you the data that you're going to read, and you provide the write data, and you can assert memory write versus memory read signals. I think it's the memory is single ported. Is that correct for the lab? Or is it just you just treat it as a black box?
It's single ported.
Okay, it's a single ported black box. So that's why you have the read versus write sequence. Whereas here, the register file is multi-ported. So you always read from these two registers. And you have a third port to the right register that you're writing to, and you can enable whether or not to write to that register. Okay, so we will assume these for now from memory. Basically, we'll assume combinational reads, which means that the output of the data port is a combinational function of the register file contents and the corresponding read select port. Make sense? You can think of this as a huge mux from the registers. And we are going to assume synchronous writes. The selected register is updated on the positive edge of the clock when write enables asserted. And that updates happens right at the positive edge of the clock. This cannot affect read output in between clock edges. It can affect read output at clock edges, but you don't care because you made your cycle time long enough. So because that's how you determine your clock, right? Okay. So this is essentially single cycle synchronous memory. That's what we're going to assume. Contrast this with something that we will see later on. Memories are not single cycle normally, right? We're going to look at asynchronous memory later on. And the memory will have a ready bit indicating whether or not a read or write is done. You're going to access memory. And basically there's some indeterminate amount of time the memory will take to give you the data or write the data to the location. And memory will tell the logic that's controlling it that it's ready by asserting a ready bit. So this is more realistic. Right? Here we're going to assume that we're able to update memory in a single cycle. Memory is synchronous and with a single cycle delay. Okay. So how do we process instructions? This is from your textbook. You probably read this part, right? This maps to those 6 steps that I described before. And let's follow this because I want to be consistent with your textbook for now. So you need to fetch the instruction. You need to decode the instruction. So this is the fetch stage. Basically, with the program counter, you access this instruction memory. And instruction memory will output the instruction. These instructions will be decoded. And control signals generated based on that decoding. And register operands are fetched based on the instruction bits, if you will. That's the other next step. Instruction decode, register file access. And the next step is we execute the instruction based on the data operands that are read from the register file and based on the function that's provided to the ALU by the decode logic, which is not shown here. Or we evaluate the memory address, depending on the instruction type, right? We can use ALU to evaluate the memory address too. The next one is fetch the operand from memory. So once we have the address, we can access memory. Right? And the memory provides the data at that address. And the next, for a load instruction, for example, you do this. And the next step, if you will, is to store the result. And the result could come from memory for a load instruction. Basically, for a load instruction, we'll take this result and write enable the register file and select the right destination register ID. And those are all provided by the control logic, right? For an ALU instruction that has a register destination, well, this data will be taken, the write back data will be taken from the output of the ALU, right? Which means that you need to have a mux on this bus. Or you need to have a pass transistor that you need to have a logic that gates access to this common bus. I don't show it here, but we will see how to construct it. And if the instruction is actually not writing any results, then write enable signal is deasserted, right? And you don't care what data gets loaded on this. Are things clear? Okay. You guys have designed this before? Yes. In a single cycle?
Not all 240 still.
Not all 240. Okay. Yes.
Going back to the slide for
This one.
yeah. why are we considering that the instruction memory and data memory are different?
Well, we do not really need to, but if they are not different, then we need to provide multiple ports. Right? You can have a single memory. This is just to illustrate the flow easily. When we get to pipelining, we will see that there's a reason why they're different, why they're separated. Because you don't want to drive the signals all the way to here, because fetch stage is located a little bit earlier in the pipeline, whereas this access is located later in the pipeline. And you don't want to send the wires all the way. But that's a good question. I mean, you don't have to have different memories as long as you provide multiple ports for the single memory. Okay, so what is to come? This is really the full data path we're going to build step by step today. Let me just give you a brief overview. So basically, this is a program counter. You fetch an instruction by accessing the instruction memory using the program counter, and the instruction bytes will be available after that access completes, so there's some time it takes to do this. And these instruction bytes are distributed to different portions of the data path to be able to process different instructions. For example, instruction byte, the bits 31 through 26 are sent to the control logic, which these are the opcode bits, right? Control logic decodes the opcode and generates the control signals that are needed to control all of these different data elements. So one control signal, for an example, is this register write signal. This signal is asserted for every opcode that specifies that this instruction is going to write to a destination register. Okay. So you can think of this control logic as a combinational control logic that checks each opcode, whether or not each opcode writes to a destination register, and sets the signal for all opcodes that write to the destination register. Okay. For each control signal, you could implement this control logic that way. We'll get back to the control logic. Let's look at the data path. Data path, so register file access. So read register. If you're reading from a register, the first register you're reading comes from these bits 25 through 21. And you remember the instruction format? This is the RS register, I think. The second register specifier comes from bits 20 through 16. Write register specifier sometimes comes from bits 20 through 16. Sometimes comes from bits 15 through 11. And I think it depends on whether or not the instruction is actually R type or I type, or load store. So this signal, register destination, controls whether this destination register ID, identifier, comes from bits 20 through 16 or 15 through 11. And that signal is generated based on the opcode of the instruction. Make sense? And similarly, the data that's read from the register file is fed to the ALU. This is the part that I have drawn over there. Right? One ALU can come from register or immediate. And immediate is generated by sign extending the bottom 16 bits of the instruction. Right? But you don't always use this immediate, right? You use this immediate only for those instructions that actually operate on immediates. And if an instruction actually operates on an immediate, this ALU source signal will be set to 1, such that this mux selects the sign extended bottom 16 bits of the instruction instead of the output of the register file. Make sense? Okay, once you have based on these, the data inputs to the ALU are determined, and ALU's control is determined. This is essentially what function should the ALU do. And this is really determined by what is your opcode, as well as something else. And that something else is not this. Oh, it is shown here. Okay, there you go. Your opcode can determine what your ALU will do. But also, if your opcode is 0, Do you remember that? If your opcode is 0, it's an what type? R-type instruction. There you go. Then the bottom 6 bits of your instruction tell you what your ALU should do, right? So there is some additional logic here that determines, based on what your opcode is, as well as what the bottom 6 bits of your instruction is, what your ALU should do. And then your ALU does whatever is specified by this control logic. And the result is, I guess the result could go to many places, right? The result could go into data memory, for example, as an address into data memory. And the result could go to a destination register as the right data. You can follow the data path, right? If this is a memory operation, if this is a load operation, you calculate the address through the ALU and input the address into data memory, and the data is read from memory. Remember, magic memory. It happens, it takes a constant amount of cycles, constant amount of time. We're still operating with a single cycle. And the data is read here. If this is an ALU operation, R-type or I type with a destination register, then you really would like to select this output of the mux, right? So if this is a load, so what is this mux for? This mux is for selecting whether the destination register value comes from memory or comes from the output of the ALU. If the instruction is a load, well, I guess here it's called mem to reg signal. If it's 1, you select the memory input of this mux and send it to the destination register. That's what it means, right? If the instruction is a load, this mem to reg signal, the control signal of the mux is set to 1, and the data that's read from memory is written into the register file. If the instruction is not a load, then this mem to reg signal is set to 0, and the output of the ALU is selected by this mux to be written into the register file. Of course, for those instructions that write to the register file, there's another signal that needs to be asserted, which is the reg write signal over here, right? So hopefully this gives you a flow of what happens in the pipeline. Well, not pipeline, the data path and the control logic. So we're designing this machinery to execute any instruction in the machine, right? So we're sharing data path components. So this ALU is sometimes used for computing the address, and sometimes it's used for computing the destination register value, right? And that depends on whether or not the instruction is a load or an R-type or I-type instruction. Okay. So if you look up here, there's something else here, right? This is, if you look at program counter, something else is happening. So how do you update the program counter? Concurrently, you need to be able to update the program counter based on the instruction specification. If the instruction is not a control flow instruction, this is easy. So what path is followed in that case? PC flows through this adder, PC plus 4. And, well, you could follow it backwards also, right? But let's follow it forward. You get PC plus 4 through this adder. And you want PC plus 4, which means that this mux signal should be 0 for instructions that are not control flow instructions. And the output comes here. And you want, again, PC plus 4 to go onto PC. So this mux signal also should be 0. So for non-control flow instructions. And then PC plus 4 flows into program counter. Right? So for non-control flow instructions, all you need to do is to set this control signal to 0 and this control signal to 0 again. So that you take PC plus 4. But for something like a jump, we will see that you will construct a jump address. This is a direct jump through the bottom 26 bits of the instruction, shifted left, and concatenated with the top, I guess, 4 bits of PC plus 4, because that's the specification of the instruction, right? You guys are familiar with this because you actually wrote the instruction simulator for MIPS. Well, actually, most of you wrote the instruction set simulator for MIPS. So that's how a jump operates. So that's how you have the data path components to generate the jump address. And the control signals should select that jump address as opposed to PC plus 4 if the instruction is a direct jump. Right? So you see that this control signal says, is the PC source a jump? And if it's a jump, then this calculated jump address is selected and input to the PC program counter. Make sense? Okay, so let's go step by step. I guess, do you guys want to take a break before we go step by step for most instructions? Okay, let's take a break for 5 minutes and just data path and control stuff. So I've already given you the basics, so hopefully you guys understand what's going on in a single cycle microarchitecture, data path and control. Are you all very comfortable with it? No? Nobody wants to say yes. Okay, so let's look at how we can start from the ground up, if you will. I've given you the top-down picture. This was the data path, and this is how some instructions operate. And believe me that each instruction that I'm going to kind of talk about today is implemented here. Of course, it doesn't implement all of MIPS instructions, and you want to implement all of MIPS instructions. But let's take a look at designing this ground up based on some instructions. Let's first implement I Type Alu instructions. And remember, these are this is the assembly notation for these instructions. This is the machine encoding. Opcode is always 0. And what you do is specified by these 6 bits. And in this case, we're going to assume that it's an add. And these are the source registers, and this is the destination register, and these bits are always 0, I think, right? And this is semantics. Semantics is if the program counter at the memory location is really this, if the data at the memory location specified by the program counter is this an add instruction, then you do the add and you increment the PC. So we just need the data path components for doing this. Let's not worry about the control logic for now. This is the control logic. Okay? Well, this is the data path that you really need for this instruction, right? You need to be able to access memory, get the instruction, divide up the bits of the instruction to, I guess, RD, RS, and RT. And you need to be able to read the sources of this instruction from RS and RT. And the ALU needs to be able to do what this instruction specifies, which is an add. So you have some control signal into the ALU that specifies what the ALU should do, and the ALU does that to the 2 source registers that are read from the register file. And the result is sent back. You need to have the data path element that takes the ALU result and provides it to the write port of the register file. And you need to have a control signal, reg write, and you need to have this asserted while you're processing this instruction. Right? So these are the data path elements you need for doing the addition. Register file access for 2 of the registers, an ALU to do the addition, and the ability to write back data to the register file. And in the meantime, there's something else that's specified by this instruction, which is increment the program counter by 4. And you need to be able to have the data path elements to do that. So we have a separate adder to do this. Well, in this case, you need a separate adder, right? Because we have a single clock cycle, and you need to be able to do 2 additions within the same clock cycle. So you cannot use a single adder to do both additions. You cannot supply 2 different signals to the same adder and get 2 different results in the same clock cycle. So you need to replicate the adder, if you will. That's one disadvantage of a single clock cycle design. If a data path component is needed multiple times by an instruction, you have to replicate that component. Right? Because you need to operate on a single clock cycle. So we have replicated the adder here. You have a separate adder that calculates PC plus 4 and feeds it back to that program counter. And the assumption is that program counter doesn't have a write enable signal because it's always write enabled at the end of the instruction, because you take single clock cycle to process the instruction. So this is all you need for the data path for an R-type instruction. And this ALU operation is really determined by the type, this field over here. Of course, to make this work, you need to set the control signals right. And the only control signals that you need to set is set this register write signal to 1, such that the write enable to the register file is enabled, and set the ALU operation correctly depending on the operation that's being performed. I'm showing add here, but depending on what operation is specified by this function, if you will, it's called a function in MIPS, then you set the signal correctly. Okay, and that's dependent on the bits that are coming from the instruction. These bits and these bits. Okay, so that's the data path. What about the data path for I Type Alu? I've already shown you, given you this, but I'm going to run you from ground up. What is an I Type Alu instruction? It essentially takes the source register, adds it to the immediate, and puts the destination to RT, if you will. And we're going to call it RT because the location of the identifier is really where the RT was for, this was the source register, remember, for R-type instruction. Now it will become the destination register for an I-type instruction. Okay? That's how the ISA specifies it. So we're going to obey that semantics because immediate occupies the bottom part, where normally R-type instructions specify the destination register. Right? So this is an example of non-uniform decoding across different instruction types. And this will complicate the hardware a little bit, as we will see. Okay, so what is the specification of the instruction? It's essentially you take one of the source registers, RS, access the register file, add to it a sign extended 16-bit immediate specified within the instruction, and also at the same time, well, it doesn't have to be at the same time, but while the instruction process, increment the program count. So what data path elements you need for this? Well, this is it. If this was the only thing we're doing, let's assume that we're doing only I-type instructions right now. Ignore the R-type. Well, I guess this is, I'll do this for you. Well, you need to have the data path to add a source register to assign extend immediate, where the immediate comes from 16 bottom bits of the instruction that you read from memory. It gets sign extended, so you need logic to do sign extension. So I hope you're able. You guys are. What do you do in this logic? Basically, you look at the top bit and extend it, right? And that value gets fed to the ALU. And you need to be able to, ALU needs to be able to specify add, just like the R-type instruction. So the difference now is you want this immediate, right? You don't want this data value coming from the second source register because this instruction doesn't have a second source register. So if you want to implement both R-type and I-type ALU instructions on the same data path, well, you need a mux, right? That's the mux I've shown you before. You need a mux that selects whether the second input of the ALU is coming from the register file or the assign extend immediate. Also, the destination register of this instruction, this I-type instruction, is coming from, I guess, bits 20 through 16. It's not coming from bits 15 through 11. That's how the instruction is specified. Whereas for R-type instructions, the input, the identifier of the destination register was actually coming from bits 15 through 11. Now you have a choice again, right? You'd like to be able to implement both. So now you have a mux that selects where is your destination register ID coming from within the instruction bits. So if the instruction is an I-type instruction, which is determined by the opcode, then bits 20 through 16 are selected as the destination register identifier. And if the instruction is an I type instruction, then ALU source is selected here. And ALU operation is specified by what the I type instruction is supposed to do. So it's not ALU operation logic becomes more complicated, right? It's not just taking, I'm not going to show you here, but it's not just taking these 6 bits, but now you need to consider these 6 bits also as part of determining what the ALU should do. So this is the data path you need to implement this is the data path you need to implement both R type and I type instructions, ALU instructions. Okay, that's clear. Now let's take a look at data movement instructions. Well, we have a load instruction, and that's encoded like this. Opcode specifies load word, and you get a base register, and you have a destination register, which is similar to I type, and that's why it's an I type instruction also. And you have an offset. Now it's not an immediate, but it's an offset, right? And this opcode specifies that it's a load word. So if this is a load word, this is what you do. You first need to compute the effective address by sign extending the offset and adding to the value in the base register. And then you need to access memory with that effective address. There's a translation step with virtual memory, which we're going to ignore for now. And read the memory at that effective address and store the results into the destination register specified by RT. And also increment program counter. So what do you need to implement this? We already have this data path that can execute R type and I type instructions. Well, okay. I guess I don't. We just need to add memory to it, right? So how do we do this? Basically, ALU operation specifies and basically we need to be able to read the base register. I guess I omitted the numbers here. But base register comes from RS again. So this is fine. These are bits 25 through 21. There's no second read register, but the destination register, so register is read here. If you look at the data flow within the instruction, the RS is read through this port, and the second input of the ALU should be the sign extended immediate, if you will, sign extended offset. And we already have this data path because we implement I type instructions, right? So we just need to set the control signals right such that this input is selected for the ALU. And ALU result now generates our address. And this ALU result should be connected to the address here. Imagine there's a connection there right now. And the data is read, so you're supposed to complete these. The read data is routed to the right port of the register file. And register file write enable signal is enabled in this case. And you need to be able to select the right destination register ID, which in this case, if you look at the specification of the instruction, is again coming from bits 20 through 16. Right? It's RT. So this is the data path you need for a load word with the appropriate connections made. And of course, to control this, you need to set the control signals accordingly. You need to set the control signal of this much such that it selects the destination register to be from RT. You need to select the control signal such that it selects immediate input to the ALU. You need to select the control signal such that ALU does add. You need to select the control signal of the memory such that it does a memory read instead of a memory write. And you need to enable the register file to be written. Okay? Store instructions, similar. Address computation is the same as load, so you can use the same data path, right? The main differences, now you take the source register and write it to the memory location specified by the address. So you don't have a destination register right now. Well, which means that if you want to implement store word, you don't need additional data path elements, right? It's the same as store. We have memory, we have address computation logic. We just need to set the control signals differently. Basically, we need to set the memory write signal such that memory is written to, And we need to ensure that register is not written to. So we need to set the register write signal to 0, not write enable. And everything else is the same as a load. Unless I'm missing something. I don't think I'm missing something. Right? Okay? So this is the load store data path, incorporating also R type and I type ALU instructions. So now we can implement R type, I type, load store, all here. Okay? At least load word and store word. Bytes, you may need to do other things, and you'll figure that out. Okay, what about non-control flow? I guess I'll leave this for you to figure out, but these are named signals. Basically, if it's a store, you enable the memory write signal. If it's a load, you enable the memory read signal. And its store is not set if the instruction is a load. Right? Okay? So this is the full data path again for non-control flow instructions. And you will figure out how to do the, I guess one thing that I really didn't discuss is this part here. This is really just load store data path, right? For ALU instructions, you need the output of the ALU to be written to the destination register, right? Not the output of the memory. So if you want to implement both ALU instructions and the load store instructions in the same data path, what do you need? You need to be able to take the output of the ALU or the load instructions and write it to the destination register, which means that you need this kind of muxing. You need a separate mux that selects either the ALU result or the output of the memory to go into the write data port of the register file. And this is controlled, this mux is controlled by the signal that says whether or not it's a load. If it's a load, you select the output of memory. If it's not a load, you select the ALU result. Right? Make sense? So that's how you build the data path incrementally by adding instructions. So let's take a look at control flow instructions. Hopefully this is very simple right now in your minds. Is it? Okay. Jump, the easiest control flow instruction. It's specified as, well, if the opcode is J, if you will, then the target program counter is calculated as the immediate shifted left by 2 bits and concatenated with top 4 bits of the PC. Actually, I think this is really PC plus 4, right? In the MIPS ISA because of the branch delay slot. You won't be implementing branch delay slots, so you will be using PC, right?
Yeah.
Okay, so this is the correct specification for the lab, but this is not the correct specification for literally for the MIPS architecture. Okay, so don't be confused by it, and I understand if you're confused by it, but we're not going to deal with branch delay slot. So what is a branch delay slot? Are you guys familiar with the branch delay slot? Yes? No? Some of you are not. So branch delay slot is one of the mistakes in computer architecture, if you will. And you will understand the full motivation of it later when we cover pipeline, really. But if you have a control flow instruction, the idea is if you have a branch instruction, or if you have a jump instruction like this, the next sequential instruction, this is a program counter, right? PC plus 4. There is an instruction here. This instruction is executed no matter what. Which means that if you have a branch instruction that's jumping to some other location in the code, this instruction will still be the next instruction to execute. And then the target instruction will be executed. Does that make sense? This is a one-cycle delay slot. So the semantics of the instruction is such that semantics of the instruction is this. You change the program counter to PC plus 4 plus whatever the specification is. In this case, it will be PC plus 4, top 4 bits concatenated with the immediate, only after you execute the instruction at PC plus 4. Yes?
What was the reason behind this?
Pipeline. So the reasoning is, if you have a two-stage pipeline, well, I haven't covered pipelining yet, but let me give you the high-level idea so that this thing doesn't sound as dumb as it sounds at this point.
Can you use thick chalk?
Can I use a chalk? So, you mean this is chalk also?
Thick chalk.
Thick.
Thick
Oh,
chalk.
big chalk. Oh, thick chalk. Okay. Thank you. So let's say you're processing two instructions in parallel, and let's say you fetch the branch, meaning you fetch the branch. You have a pipeline stage. You do part of the branch here, and then you're going to do next part of the branch later. Now, branch moves to the next stage in the pipeline. To keep the pipeline full, let's say you're doing adds, right? Let's remove the branch here. Add 1, add 2. You could do a portion of the add here while you're fetching. Let's say this is the fetch stage and this is the execute stage. While you're executing the previous add, you can fetch the next add. So this is the concept of pipeline. You can increase concurrence. Now the problem with pipelining is, if you have a control flow changing instruction, if you have a jump here, now jump can go to the execute stage, next stage, and you can do something about it. But what do you fetch next? You're changing the control flow, right? And you may not have, especially if this is a conditional branch, you may not have the address available for the next thing. Now if you have a branch delay slot, if you define the branch such that the next instruction is always executed, you always know what to fetch next. Does that make sense? If this is not very clear, don't worry about it, because we will get to pipelining in more detail. But delay slots are introduced such that you always know what the next instruction is, so that you don't need to worry about what to fetch in the next cycle in a pipeline machine, because you always know the next instruction you're going to always execute. Make sense? The goal is to keep the pipeline full. Now, of course, in a machine like this where things are not pipelined, it makes no sense. Right? Okay? Yes?
So what do you do with that extra one that you fetch because you're dumping somewhere else?
Well, the semantics say you always execute this, which means that the compiler or the programmer needs to ensure that there is an instruction here that's always executed.
And that's not going to alter.
That's going to alter the state such that it's consistent with the semantics that they intend, right? And if there's no such instruction that you can place here, what do? Exactly. Okay? So you will not worry about the delay slots because of this reason in your lab. But some of the things that I will show here, I think will unfortunately incorporate PC+4. Not this one. Okay, so what do you need to implement the unconditional jump? Let's see. Well, okay. So we're going to build on the data path that we've designed before. To be able to implement this, well, you need to ensure that the jump doesn't write to the register file, right? There's nothing in jump specification to write to the register file, so read write signal is 0. You need to ensure that memory read and memory write signals are 0. Actually, you don't really care about the memory read signal, right? You just need to ensure that memory read write signal is 0. So this could really be don't care also. ALU operation you don't care about, ALU source you don't care about, and this mux is omitted here, but you don't care about that also because this part of the data path you're not going to use. And as long as you don't do something bad that changes the state here, you're fine. Right? So we're going to ensure that we're not going to change the state if this is a jump. And we're going to deal with this part because we're going to update the program counter. That's what this instruction specifies. And this is what you need to be able to update the program counter. Now your program counter is not only coming from PC+4, but it could come from, if it's a jump, it could come from PC top 4 bits concatenated with bottom 26 bits of the instruction that are left shifted by 2. Actually, to be correct, I would have left shifted here by 2. And that's the source, that's another possible source of the PC, input to the program counter. And if the instruction is a jump, this input is selected. Make sense? So you need this data path component to be able to implement this jump instruction. What about other things that you will need to worry about? Jump register. Now I have to remember what jump register is, but it's a register-based jump, right? So I'll look at my cheat sheet. Hopefully you guys have this cheat sheet also. JR, jump register. It's an R-type instruction, and basically it does this. PC equals register RS. I guess. So what do you need to implement jump register? Basically, you cannot update the program counter with PC+4 or this. You need to be able to have the ability to read a register if the instruction is actually a jump register, read the source register, take the data, and place it into the PC. Well, you need to provide that data path. And you need to set the control signal such that now it's not anymore is jump, but you have 2 bits in your control signal. And if it's a jump register, you need to select the appropriate control signal. Well, what about jump and link? There's an interesting one here. Jump and link does this. Program counter is equal to exactly this, jump address. And this cheat sheet calls it jump address. But it also does something else at the same time. It says R31 equals PC plus 4, is that correct?
Yeah.
Well, PC plus 8 because of the delay slot, but I think in your lab you'll implement PC plus 4. So what do you need? You already have that. If an instruction is a jump and link, then you already have this data path for this. You're going to select this input to the PC because the PC is specified exactly like this as part of the instruction execution. But you also need to set register 31 to PC plus 4. So you need to be able to have the ability to take the PC, the data path where that did not exist before, until we consider this instruction, and put it into the write port of the register file, and also set the write register ID to 31, right? So now you're going to extend the muxes that are already here. Make sense? That question mark is for you to figure out. Is that clear? So the specification of the instruction now requires an additional data path that could take the PC, put it into the write data port, which means that you need to mux this write data port with whatever data was coming here. And your write register, you should have the ability in your data path to set the write register to 31 if your instruction is jump and link, which means that there needs to be another mux here. This mux, remember there was a mux here that's selected between RS and our destination. Now there needs to be a third input to that mux, 31. Right? And if the instruction is a jump and link, you select the 31. You don't select RS and RD from the instructions. Okay? Conditional branch instructions. Well, looks like we're already over time, but maybe we should stop here and we'll implement the full data path and start with the microcoded architectures next time also. Okay. Please do the reading.